All right, all right. How are we doing today, y'all? Someone's getting a phone call. Someone's important. Let's see. Should we answer it? Nah, too late. All right. We have 14 views on YouTube of this video. Are any of y'all any of those views? This was Ashley sent this out on Monday. This is me going over the amino acids on your hand. This was what that was supposed to be. So hopefully this is helpful for y'all. Let's turn the volume on. So the back of our hand is all of our non-polar amino acids. I'm going to be teaching all the amino acid tricks on how to remember it on your hand. So the back of our hand is all of our non-polar amino acids. Starting off, we have glycine, alanine, proline, valine, methionine, leucine, and isoleucine. Our middle finger is going to be methionine because it's sulfur containing. Sulfur smells very badly. This is a bad finger, methionine. Next, we have our branched chain amino acids, valine, leucine, and isoleucine. Lastly, we have proline. Proline is the only amino acid that doesn't have a free R group, so it's all the way over here by itself, proline. Once again, those are all of our non-polar amino acids. On the palm of our hand is going to be our polar amino acids. We can grab the pole with this part of our hand. We have serine, threonine, cysteine, asparagine, and glutamine. Cysteine is sulfur containing, so for the same reason as methionine, sulfur smells bad, cysteine has sulfur, so these two are our sulfur containing amino acids. On the palm of our hand, we're going to have tyrosine, phenylalanine, and tryptophan. These three are our aromatics. So when we go to smell something, we smell it with the palm of our hand. So tyrosine, phenylalanine, and tryptophan. Tyrosine, serine, and threonine, these three are our hydroxyl-containing amino acids. So all three of those go together. And lastly, asparagine and glutamine, those are our amide-containing amino acids. So that's it with the hand. For our positive and negatively charged, our positive charge, we have our really good friend Hal. He's a great guy, very positive personality. So histidine, arginine, and lysine are our positive amino acids. And our negative ones, nagging is a negative trait. And so we have aspartate and glutamate are negative. So nag, negative. Thanks. Right? Don't clap. That's terrible. So that's like broken down real easy for those of you that have it on your hand. And actually email this out to y'all's entire try along with the regular podcast from last week. So that's in your email. It's just a YouTube link that's within that email. So feel free to check that out as many times as you can. Let's see if we can get that up to like 1,000 views, right? Be famous? No. Cool. And then don't forget glycine. I don't have that on there too, but glycine is the only one that's achiral, right? So glycine was all the way down here, glycine, alanine. And that should be pretty much everything from that test, from those parts. Is that helpful? Does that seem like it might make it easier for some of y'all? Cool. If one person has helped, that's perfect. All right, I told y'all last week that this is going to be hopefully a little bit of a review. We'll find out. I forget how long Chapter 4 is, obviously, because I'm turning so many freaking pages. Chapter 4 is like, what is that, 20 pages? So we're going to try to get through as much as possible, or we're going to see maybe on Friday at 11 o'clock, or maybe Tuesday during lunch, I'll hold like another review session for us, just in case we don't have any time to review at the end of today. When? Tuesday? Is the test Tuesday or test Wednesday? Hopefully on Friday. It's after lunch? I think y'all are going to be probably like cramming beforehand, so.
Tomorrow, Thursday?
Yeah, Thursday doesn't work. Tomorrow doesn't work for me personally, but if anything, I can just podcast it and send it out to y'all for those of you who can't show up on Friday. I'll show of hands who here could be here on Friday at 11 o'clock. Okay, of those who could be here, who would actually show up here on Friday? Oh, that's good. That's cool. There's a big difference sometimes.
All right. So from last chapter, definitely need to know our primary, secondary, tertiary, quaternary structures. Just quickly going through that. Need to know. Ooh, that's still on YouTube's. Cam. This will pull up perfect. Need to know our structural classifications of proteins. Remember which ones are fibrous and which ones are globular, right? So globular are water soluble, so that's going to be our myoglobin, hemoglobin, whereas our fibrous are insoluble, so that's going to be our collagen, keratin. We use our hair and nail examples there. Integral membrane proteins are part of that cell membrane. Proteins embedded within the membrane. Amino acids are polymerized with condensation reactions. So that means that we remove a water to make a peptide bond. Condensation, water forming. Primary structure determines, let's see, it's our the amino acid sequence. So we use that rubber band example, or the necklace example. It was each individual pearl. Sorry, I'm just trying to go kind of through this. Those are peptide bonds, disulfide linkages. Those are covalent, right? Primary structure determines the overall function of the protein, right? Each amino acid sequence determines the overall function of the protein. Secondary structure, this is where it kind of got a little bit contradictory with cells and tissues, but for our purposes, secondary structure are alpha helices, beta pleated sheets formed with hydrogen bonds, right? Hydrogen bonds, just going to say it again, you have a partial positive on one hydrogen and the partial negative on a electronegative, like oxygen or nitrogen, what have you, on a separate molecule, and those are attracted to each other. That's our hydrogen bond. Alpha helices, the right-handed ones are more thermodynamically stable. If you're not right, you're not right. Beta pleated sheets, anti-parallel is more stable than parallel, and that's just because of the different bondings. Glycine and proline are what form the beta turns.
Did you forget about the anti-parallels?
Anti-parallel beta pleated sheets, so when they run in opposite directions, so the N going N to C, the amino side to the carboxyl side going that way, our amino side, carboxyl side going that way. When they're running opposite, just like DNA, it's more stable. Whereas when they're parallel and they're both going the same direction, that's less stable. Tertiary structure is the overall 3D structure of just one polypeptide strand, right? And they form motifs. So alpha helices, beta pleated sheets can form motifs. And quaternary is just when you have a bunch of different polypeptides coming together to make the overall protein. So example, hemoglobin, right? Hemoglobin has how many parts to it? 4. How many does myoglobin have? 1. Good, we'll get there in just a second. Need to know what a native protein is. So proteins that are in their functional and folded conformations are native proteins. Loss of native structure is called denaturation. When you get it back, that's called what? Renaturation, right? Just change one letter. Need to know that nonpolar residues are on the insides because they don't have poles. They're hydrophobic, so they're water-fearing. So our cytosol and our blood is pretty polar with all the water in it. So our polar residues are on the outsides, interacting with all that stuff. Nonpolar on the inside, getting away from it. It's in its shell, scared. Where are we at? Remember we changed this to weak up here? Extremes of pH, strong acids and bases, and extreme heats can permanently destroy native proteins, right? So permanently with all of our extremes. Whereas our like weak bases, small changes in temperature, what have you, they can just denature them, but they can spontaneously renature. We talked about a little bit of innate intelligence with that also. All right, comparing myoglobin to hemoglobin. All right, myoglobin monomer, so MM monomer. Myoglobin present in muscle, that should give it away with the prefix myo, and that's oxygen storage. Hemoglobin tetramer, we already talked about, present in red blood cells, and that's oxygen transport, right? So hemoglobin takes oxygen from our lungs to our tissues and deposits it there. Hemoglobin has two alpha and two beta chains. Oxidized myoglobin is called metmyoglobin, and that cannot bind oxygen to it. That's pretty important. Myoglobin is for oxygen storage. All right, we talked about our dissociation curve. We have board reviews right now, actually, all this week. And yesterday we were talking about physiology, and we went over this curve. It's going to show up later. And we talked about how pH and 2,3-BPG and heat and carbon dioxide all affect this curve. So it's going to show up later. One thing that he showed us, so just looking a little bit forward here, if you want to change pH, so when we lower pH, we're getting more acidic, right? If we're getting more acidic, we're getting more free hydrogens in solution. All right, so if you want to just say increase hydrogens, so they're all increasing. Can y'all see that? Yeah. So if y'all want to switch decrease in pH to just increase in hydrogens, so everything's going up, and then concurrently change this to just a decrease in free hydrogens floating around, so everything's just going down, causing left shifts. That was how he had it written down. Just another way of looking at it. Where are we at? This oxyhemoglobin. If you ever see an oxygen or hemoglobin, and he's talking about a curve, he's talking about this one. It's sigmoidal, right? It's kind of S-shaped. And we said that myoglobin has a hyperbolic. Need to know these boxes that are comparing myoglobin, hemoglobin, but a lot of this is repeat. Myoglobin, one globin chain, binds only one oxygen. It's got a higher affinity because it's storing it. It doesn't want to get it away, it wants to keep it. So high affinity for oxygen, myoglobin, and produces hyperbolic curve. Whereas hemoglobin, there's 4 chains, so it can bind 4 O2 molecules, lower affinity for oxygen because it's got to get rid of it at the tissues once it gets there, and produces a sigmoidal, that S curve. Cooperative bonding, we talked about this, 10 state versus relaxed state. So once that first one binds, it's more likely that all the other ones will bind. Once it loses that first one, it's more likely it'll lose all the rest of them. Oxygen binding to hemoglobin is allosteric. Talked about that. Talked about these shifts. Need to know, he's for sure going to ask a test question of which of the following doesn't cause a shift to the right. So you're going to have to be able to pick that out. So shift to the right, everything goes up, except pH. Or a shift to the left causes everything to go down, except pH. Fetal hemoglobin, it has a higher affinity for oxygen. We talked about this in boards yesterday too. It's amazing what actually shows up. So it's kind of cool, but also kind of crazy. It's a tetramer, but it's got alpha 2, gamma 2. So what did regular adult hemoglobin have? Alpha 2, beta 2. So hemoglobin is alpha 2, gamma 2. Has a higher affinity. Sickle cell anemia, we talked about this yesterday, has a lower affinity for oxygen. has that sickle shape, and that's alpha 2, beta, sickle 2. That one probably won't be on the test. Any questions from last week? I know I just flew through that, but.
With that last part with hemoglobin, you said normal is alpha 2, beta 2?
Yes.
Okay, and that's for, I was thinking female.
Yeah. Fetal, not female, yes.
Fetal. Okay. And why is that important?
So why is that important? One, he could ask it. Two, when you're kind of looking at the different physiologies of like a newborn versus like a 2-year-old. So if you know that, I think they said like for the first 6 months of their life, they have this higher fetal hemoglobin because a lot of the times, while it's in the womb, its nutrients are coming from the mom, and red blood cells last about 90 to 120 days. So it's going to take time for those red blood cells to, I guess, be recycled and have adult ones made. So you have these different oxygen binding capabilities within the newborn. So its energy needs and weight it takes oxygen from its lungs to its body are going to be different than you and I now. So just understanding how the newborn's cardiovascular system works is kind of important. Does that answer the question?
Yep. Thank you.
Cool. Any other questions? Yes.
Does the higher affinity for oxygen mean it wants to store more?
It's going to hold on to it longer. Yes.
Actually, sickle cell. So, do we have to know a lot about that, or just the fact that it changes from glutamate to valine, and why is that?
So I think I just underlined the glutamate to valine because we talked about the primary amino acid sequence determines its overall function, right, for a protein. I guess for an enzyme as well, but for this protein. So this changing of the amino acid sequence changed the overall structure and function of that protein. So just that one change in glutamate changed the overall 3D structure enough to where when that oxygen binds, it's not as strong. So he's not going to ask, I don't think he's going to ask you like which one changes or anything like that, but he might. I doubt it, but he might. So just know that there's a less affinity and there's a change in the amino acid sequence. Cool. Y'all look destroyed. Did y'all have cells and tissues today?
Yeah.
Was that great? Did that go well?
I have micro.
All right, well, we'll try to have fun, as always. I got dum-dums today, so if you miss it and it hits you in the eye, there's more damage that can be done. That's on you, though. It's not on me. Be better athletes. But,
That's practice.
yeah. All right, enzymes. How far through Chapter 4 have y'all gotten? Not very far. Perfect. 54? Okay, somewhere in the 50s. Cool. Enzymes. Enzymes are really important. They make our body work so much more efficiently than if we didn't have them. To give an example, it's like if you're trying to hang a picture, or you're like hang a curtain rod, like I was doing the other day. If you don't have enzymes, you're just using like a screwdriver to put that screw in the wall. But if you have enzymes, you can just use a screw gun and just get it done a lot faster, a lot easier. So it makes life a lot easier. All enzymes are proteins. That's why we learned proteins, and now we're learning enzymes, because all enzymes are proteins. And they, like I said, they are biological catalysts. And they have specific functions. So an enzyme that is helpful for our heart is different than the enzyme that's helpful for our liver, which is different than the one that our brain will use, what have you. So they're all very specific. So they're specific for their substrates and products. And they increase the rate of biochemical reactions by, this is kind of the more important part, they increase the rate of biochemical reactions, decrease the activation energy, or lower the free energy of biochemical reactions. So we'll get to that here in a little bit, but just know they make it easier, they make it faster, and also, it's important here, the native nature of enzymes remain unchanged before and after completing of reactions. So what that means is, like, once an enzyme is used, it's not, it can still be used for another reaction after it. So it'd be like, let's see, if I'm using that screw gun, right, to put the nail, like to put the screw in the wall, I can use that same screw gun to put the next nail in the wall, and the next one, and the next one, and the next one. So that enzyme is still there to be used for successive reactions to be done in the body. All right, cofactors, coenzymes. Some enzymes need other things to make them work, and these are those other things. So to stick with the construction example, if you have like one of those shields that you can put on to keep the screw where you want it without it falling off, that could be like a cofactor or coenzyme, or like having an extra battery to keep it going. But cofactors are, all they are metal ions. That's it. So all your metal ions are cofactors. You're going to need to know these, differentiate this on the test and boards. Cofactors are your metal ions, and that is all on this next page. We have copper, iron, potassium, sodium, magnesium, manganese, selenium, zinc, and molybdenum, I think, is the last one. The biggest ones that we use in our body, for actually hands down, is going to be magnesium, is the most common one, and manganese is going to be probably the second most common that we'll find with what we're doing here in Try 1. But cofactor, metal ions. So anything that kind of has a charge on it or is on the periodic table. Our coenzymes, all those are like our vitamins. So on the top of this page here, we have our coenzymes. We have biotin, vitamin B12, folate, which is B9? Is that what I heard someone say? No? Whatever. It's an enzyme. I need to know these. You need to know those for boards too. Obviously, I have a little bit more studying to do. But coenzymes, cofactors, need to know them. Cofactors, metal ions, coenzymes, vitamins. Easy, easy test question. All right. Enzymes. There's just a little bit of definitions, so please just bear with me. This usually trips people up on the exam because it's just kind of a lot of the same word. A hollow enzyme is the active form of an enzyme, a hollow enzyme. So like a hologram, right? That's like an active, you can see the person doing their thing. Like in Star Wars Episode 4, right? See Princess Leia, she's a hologram. I made my girlfriend watch that for the first time. She'd never seen it. She's like 25 years old. Can you believe that? I couldn't. She almost fell asleep. I was not happy. Anyway, so hollow enzyme is the active form of that enzyme. All right? An apoenzyme is the inactive protein part of the enzyme. So A meaning like not. So A is not active enzyme. So hollow active, apoenzyme inactive. But if you combine a coenzyme or cofactor to that apoenzyme, you get hollow enzyme. So it's kind of a little bit of an equation. So apoenzyme plus cofactor or coenzyme, depending on what it needs, equals hollow enzyme. or holoenzyme equals apo enzyme plus coenzyme cofactor. Having those sorted out is really easy, but if you can just remember that holo is active, right? A hologram is fully functioning, working. You can see it. It's a person. It's right there. And if you can remember that the prefix a typically means like without or not, that's the inactive one. A prosthetic group, this also trips people up a little bit. It's pretty much just anything that's not an amino acid that's covalently bound to an enzyme. So that can be a carbohydrate, that can be a fat, whatever. It's just anything that is not an amino acid that is covalently bound to an enzyme. Right? So for people who have prostheses, they have the prosthetic part of their leg. We actually have a guy in our class who has one from like here down. It's really cool. His like at the very end of it, it's just like a stub right here, and they put his calcaneus right there, and then they were able to attach this anterior tib muscle, and so he can kind of like wiggle it a little bit forward. It's kind of cool. We were an activator, and some of the people still didn't know he had a prosthetic leg, and so we're doing leg checks, and so this girl like rolls up his pants and like sees it and like freaks out because she didn't know it was there. Anyway, so that's a prosthetic group. Coenzymes, they can help with stuff. We'll get to these types of reactions here in a little bit. Yes. We'll get to this, yes. All right, we talked about this. Just know that he's probably going to ask you, like, which of the following is or is not a cofactor or coenzyme. So if you see anything that says metal, if there's like 3 metals and like something that's clearly not a metal, pick the one that it's not, vice versa. Cool. Nomenclature. This is really important. If we can understand this, the rest of when we get to Krebs cycle and glycolysis, it's going to make it so much easier. I promise you, just remember this, and I'll explain it again later. But when we name an enzyme, the first part indicates the substrates. So that's talking about what we're starting with. The second part indicates the type of the reaction that's going to do it. So when we look at an enzyme, we'll start with hexokinase. Hexokinase. That's our first enzyme. Let's just skip ahead to it real quick. I'm not good at skipping. Here we go. Okay. Hexokinase is our first step in glycolysis. Hexo meaning 6, right? We learned that in like 5th grade. Hexo meaning 6. Kinase just means the transfer of a phosphate. So we can see that glucose, and we'll learn this later, glucose is a 6-carbon sugar. So hexo, 6-carbon sugar. Kinase meaning we're transferring a phosphate. We're transferring this phosphate from ATP onto glucose, making glucose with a phosphate on it. So it tells you, the enzyme name tells you everything that you really need to know about it. It tells you what you're starting with and what you're doing to it. So just keep that in mind. It makes a lot of sense if you think it through, but when I was taking organic chemistry, I was also taking Russian, and I was taking anatomy. So I was learning like 3 different languages at the same time, which is kind of similar to what y'all are doing, right? You're learning biochemistry, anatomy, and cells and tissues, or I guess even chiropractic on top of that too, and learning about who you are, like your own language of who you are now too. I struggled really hard with that, but I didn't know these kind of little tricks that if you can just know what each of the parts of the words mean, and then you can just combine them and like piece them together, like and look in the middle of the words and like, oh, I know what this means. It makes it a lot easier. It is. It's just not a specific one.
Okay.
It falls under transferase.
It's underneath transfers. Okay.
Yeah. Other questions? Cool. So, need to know these, need to know these, need to know these. There's going to be at least 2 of these on the test. Oxidoreductase is the transfer of hydrogens. Okay? So all this is, these are our oil rig or redox reactions, oxidation reduction reactions. That's all they are. So that's class 1. I think he said don't know the numbers, correct? Or did he say anything about that at all? He did? He said you do need to know them?
Number 1 is always oxidation.
I'm pretty
Number
sure
2
you did
is
say we
always
have to know.
transfer.
Okay, so make sure that you know the number that goes with it, because he could just ask, what's an example of, or what is the name of a class 3 reaction? And then you'll just have whatever, a 1 out of 6 chance of getting it right, if you don't know it. All right, so oxidoreductase is all just our redox reactions, transfer of hydrogens. You'll have an enzyme that typically will say dehydrogenase on it. Then that's on the next page if you don't want to write that down. Transferase, all you're doing is transferring a group, right? We learned all our groups in chapter 1, right? Like our sulfhydryl, our phosphate groups, our hydroxyl groups, what have you. So that's just taking one of those and putting it on a different molecule. Transferase, transfer stuff. Pretty simple. Hydrolase, so hydrolysis of a substrate or breaking of a chemical bond with the use of water. So for those of you who know like what pressure washing is, right? You like high pressure water and you clean the concrete. I did that for my dad for the summer. You clean concrete with it or clean whatever with it. It's just using that water to break apart a bond. Pressure washing isn't a hydrolase reaction, is an example. Lyases is the breaking of bonds with everything but water. So water has its own special one. Water is pretty important. So it gets its own classification, and we can signal it out because it says freaking hydro in the name. Pretty simple. Lyases, it's a little bit harder to figure out, but it's the breaking of bonds without the use of water. Isomerases, iso meaning what? What does iso mean? Same, similar, what have you. So it's the transfer of groups within molecules to form isomer forms. So it's taking some kind of, probably like an OH over here or a hydrogen over here and putting it over here on that same molecule. For the faces that I just got, if you have like an OH over here, that's your molecule, enzyme comes in, your isomerase, and now it's over there. All it is just changing it. So an example of that would be like glucose being turned into fructose. So taking it from the aldehyde to the ketone. We'll get to it. We'll get to it. And ligases, this is the only one. This is the formation of carbon bonds by condensation or with the use of energy. So ligases, making bonds. It's difficult to making sure that you have lyases versus ligases. I don't really have any good ways of remembering that, but that's important to get those different from each other.
On lyases, doesn't it say that it form or breaks two double bonds? Not ligases, lyases.
Lyases, the breaking of chemical bonds.
But below that.
Okay, yeah, I mean, mainly it's the breaking of the bonds, breaking of carbon bonds, but also if you want to say the formation of double bonds or ring structures, you could.
Liars break.
Yeah. Liars will break your heart.
Yeah.
I like that. I like that. Good. So, and we'll go over here. Those are on the next page as well. But he said, don't worry about this, yes? Did he tell y'all to cross that out? He did not tell y'all to cross that out?
He taught us that.
I don't know that, so we're just going to pretend like he skipped that. I don't think, that was not on our test.
In my book also is.
He told us to get rid of it, yeah, so I guess last try, or he told you to get rid of it too. So, I don't know, maybe ask him like, hey, is this something that we really need to go over? I can't help you with that. That looks awful. All right, so once again, these are really, really important. We're going to need to know these. So why we're doing this is when we get to glycolysis, when we get to the Krebs cycle, we're going to have all these enzymes doing, obviously, their jobs. And he can ask you on any exams, or even boards is going to ask you on all these exams. We went over this last time too. What type of enzyme classification is the enzyme phosphofructokinase 1? And you're going to be like, I don't know, I didn't study that. Or you can be like, of course I studied that. It's a whatever kind of bond. Actually, I think it's a transferase. Yeah, it's a transferase. Anyway, but so when we get to chapters 9, 10, 11, there are different enzymes that we're going to need to know, and we're going to need to know our types of reactions for them. So if you understand these types of reactions now, and you do well on this test with this, good for you. If you were like me when I took this class, and you didn't understand these well, and you just tried to like guess and reason through all of it, it's going to be a little bit harder for you. So just try to understand it now. Oxidoreductase. What does that deal with? What are we changing, moving around? Redox reactions, we're taking hydrogens and moving them around. So, the transfer of electrons or hydrogen ions. Mainly, we're going to be doing the hydrogen ions. He could ask you any of these other words: oxidase, dehydrogenase, reductase, probably less, won't say this one, but monooxygenase, dioxygenase. The one he likes mostly are the dehydrogenase and reductase ones. He likes those a little bit better. Dehydrogenase is going to be awesome if he picks that one because most of those are the types of enzymes that we'll see later, is typically the dehydrogenase. And all that's doing is taking a hydrogen that's on, let's just use this example here. So we've got ethanol, okay? Ethanol, pretty simple, 2 carbons with a, what kind of group is that?
Alcohol.
Alcohol, right? Good. All this is doing is we have this NAD coming in. Is that a coenzyme or cofactor? Is it a, do we see this on the periodic table? No, right? So this is a coenzyme. It's not magnesium, it's not manganese, it's not a metal, right? So if it's not a metal, it's a coenzyme. Good.
So normally we have like magnesium. NADH is what? Or NAD is what?
Coenzyme. It's number 2. It's vitamin B2. I forget. Maybe B3. It's a vitamin, is all it is. I can get my board notes out here at our little break. But it's just a coenzyme. It's a vitamin. And all it is that comes over and it takes that hydrogen. It takes a hydrogen
Right there on
and takes it away.
Page 48, NAD, niacin,
Niacin
coenzyme.
nicotinamide. Good, thank you. And all that coenzyme's doing is it's taking this hydrogen and taking it away with it, making NADH, leaving you with acetaldehyde. So all it's doing is taking the hydrogen from ethanol and says, I want that, and it takes it, and then that leaves you with acetaldehyde. Question? Yeah, it did. We'll get to that in a further chapter. Just understand now with dehydrogenase, removal or addition of hydrogens. Cool. Good catch. Not worth your time right now. So how this test is going to work is he is probably going to ask like this specific, like one of these examples here. So y'all are going to need to know that ethanol, the conversion of ethanol to acetaldehyde falls under oxidoreductase or dehydrogenase. So that's going to be just a little bit of memorization on your part, understanding those words and those molecules, or just remembering those words and molecules. But looking for keywords such as the removal of hydrogen or oxidation reaction or reduction or reductase. If you see any of those words, you know that's class 1 oxidoreductase. So you're looking for those keywords. But also, I didn't do this when I took the test, and I had to like really reason and use my OChem knowledge. So for you don't have that OChem knowledge, try to remember these words. It'll make your life a lot easier. Yes? ADH. So that's, so on top, so there's good, yeah. So way to point it out. So on our top here, we're going to have our coenzymes, cofactors. Those are going to be on the top, or things that are coming in and out. And whereas on the bottom, that's going to be our enzyme name. So the name of the overall enzyme is going to be on the bottom. And on the top is our cofactors, coenzymes. And that should be universal throughout the rest of this book and eternity. That's not official enough. Cool. Oxidoreductase. Transferase, like we said, transferring a group. So here we have hexokinase, right? We talked about this just a second ago. We're taking glucose, which is a 6-carbon molecule, and we can count that if you want to check it. 1, 2, 3. Each one of these points is a carbon. 4, 5, 6. So a 6-carbon molecule. Kinase, meaning transfer of a phosphate group. So it's taking this ATP, which is our energy, adenosine, triphosphate is what that means. So it's just A, phosphate, phosphate, phosphate. There's 3 of them. It's taking one of those phosphates and putting it onto glucose, making it glucose 6-phosphate. And the 6 just means to put it on the 6th carbon. We'll get more specific on that later. But overall picture, transferase, taking a group transfer, taking a group and putting it from one molecule onto another transferase.
So that's why it becomes ADP?
Yes.
Instead of 3 has 2.
Exactly. So that's taking adenosine triphosphate to adenosine diphosphate. Tri meaning 3, di meaning 2. Because that phosphate is no longer on it. It's now all the way over here.
So is the ATP or
The magnesium is going to be the cofactor because it's a metal, right? And I guess ATP, ATP is not, it's kind of a part of the reaction. If anything, we'll say coenzyme. We'll say coenzyme for right now. Cool.
Why does OH become OPO3 2 minus?
Because the phosphate group replaced that OH group.
Oh, so the P is not just a P, it's PO4 minus or PO3.
Actually,
PO4 minus, right? Thank you.
cool. Hydrolase, hydro meaning what? Water. All right. So we're going to be breaking bonds with water. That's really all he's going to ask you on that one. So we're breaking bonds with water. Remember, breaking. They're breaking bonds with water. Remember the pressure washer. It's removing that dirt from the concrete. It's breaking it up. Lyases. Lyase is the removal. this is the breaking of carbon-carbon bonds. So this is the first time we're breaking. The second time we're breaking bonds, but just not with water. It's every other way except with water. So understanding. So we got here. We have a double bond, and we're breaking one of those bonds, making just a single bond. No, it could be. There's always going to be one carbon involved, yes. So in this instance, there were two carbons, so it's this carbon-carbon bond here, but it could break carbon-oxygen, carbon-nitrogen, carbon-sulfur bonds. Carbon's going to be involved, yeah. Isomerase, isomer meaning what? Same. So here we have our enzyme, triose phosphate isomerase, also in glycolysis. We'll get to it, but all it is just it's moving around this OH group. It's taking the OH group that's here on the top and making it move over here to the middle. It's just changing it within the thing. So if you ever see an isomerase within the enzyme, you know it's class 5. Or if you see anything where it says making an isomer, that's what you're looking for. Sorry, I'm kind of blowing through this fast, but we have a lot to get through. And ligases, remember ligases, this is where we're making bonds. Okay, this is the first time we're making bonds. So if you see anything, so here on the right, or here on the left, we have our enzyme in blue. And on the right, we have biotin, which is our coenzyme cofactor. Biotin. Is it a metal? No, then it's a coenzyme. Good, right? Biotin is not on our periodic table, so just ask yourself, does this look like it could be on the periodic table? The answer is yes, cofactor. The answer is no, coenzyme. Cool. And we'll go over that again next time we meet, but we just need to get through that. Are there any pressing questions? Need to know them, need to know them. Spend just that 30 minutes or 5 minutes in between each class just re-looking over those, trying to specifically memorize these different types of reactions, these different named reactions. It'll make it easier for you. All right, enzyme. Let's take 7 minutes. 7 minutes and 36-second break. All right. All right, what page did we end on? Page 52. Got like 16 more pages and like 50 more minutes. So it's going to be a lot of fun.
16 pages of this.
Potentially, yeah. All right, enzyme chemistry. Need to know these words. It'll make your life a lot easier. Enzymes are just our catalysts. They speed up our reactions. That's what enzymes are. Substrates are what bind to our enzymes. So substrate is what binds to enzyme. So that's like our starting material. So substrate, our starting material, it's what binds to an enzyme. And we have our cofactors, coenzymes, is what enzymes need these in order to work. Right? Cofactors are our metals. Coenzymes are our vitamins. Good. There's a nice little picture that's color coordinated. And this picture is just showing you how it's specific. So only the triangle fit, the hexagon won't. So enzyme, substrate, cofactor, coenzyme. Cool. They're very specific, like everything else in our body. You need to have the right geometry, the right 3D shape, and the right charge distribution. So having a positive, negative charge, or polarity at certain points is what's going to need is how that enzyme and substrate are going to bind together. It's just like your 3D shape. Specific 3D shape.
Charge distribution is like the 2 plus has to be with the 2 minus.
Yeah. Or like or having a polarity on one part matches with the polarity on the other part of the enzymes. Like polar forces are right and nonpolar forces as well. Just stick with the charge. Yes, the 2 plus has to mix with the 2 minus perfectly.
Okay.
Yes. It's important here, enzymes and substrate binding is due to non-covalent forces. So those are the ones we talked about. Van der Waals, electrostatic, we haven't talked about that, but charges pretty much. Hydrogen bonds and hydrophobic forces. These are non-polar, non-covalent forces, right? Because how enzymes work, in order to like reuse it, we're going to have to like detach, right? If I want to reuse my screwdriver, I'm going to have to actually like take it off the screw and like put it on a different screw. So if we did a covalent force for enzymes, that's pretty much a permanent bond. And then we could never really use it again. So non-covalent bonds for enzymes and substrates. Lock and key model, this was on our test when we took it. Pretty much it kind of just goes through each of the stages of how the substrate binds to the enzyme and how the products are formed. It's pretty simple if you can just get the overall picture. So this is kind of the equation or flow chart. So you have your E plus S, and he'll ask it like just E plus S in these letter forms. But E means enzyme, S means substrate, right? So they're separate. Next, they combine, so they're just ES. And then, since when the substrate binds, the enzyme's able to work, right? So it does its thing, and it makes its finished action. So we're starting off with screwdriver, nail, separate, put them together, right? Enzyme does its thing, or screws in the wall. So we have and the screwdriver still attached, so screws in the wall. So that's our EP, our enzyme and product. And then you take the screwdriver off, product plus enzyme. Then you can do the whole thing, and you can do it again. So he would say, put these in the right order. So he'd have like that one first, then that one, and that one, and that one, and then that would be A, and then B would be that, C would be that, and then D would be that. So you would know, you just need to know it's E plus S.
That's eight.
What?
That would be order 1, 2, 3. Is that the correct order?
The order is this is the correct order that's in. So we know that we're starting off with our substrates. We're starting with our substrates. We're finishing with our products. We're starting with our enzyme and substrate separate. We're ending with our enzyme and product separate. So if we can know that we're S is going to be where we're kind of starting. P is going to be kind of looks like an F, so that's where we're finishing. And they have to start separate. Good to go. And here's just another way of showing that pretty much. Function of enzymes is to increase our reaction rates. Increase reaction rates. And when it says the reaction equilibrium is not affected, all that's saying is that we can reuse our enzymes over and over and over and over and over again. We have too many things in our body to have too many chemical reactions happening right now, probably millions of chemical reactions, if not billions, happening right this second in each and every one of us. That would take way too much energy to make and destroy enzymes, and we could just say, hey, like, let's just reuse them. Like Legos, right? You just put them together, take them apart. Put them together, take them apart. They have to be close enough to where they can actually have those forces, like those van der Waals or hydrogen bonds, so that those forces can actually come together. So all that's really saying. Next page. All right. A lot of people who haven't taken chemistry get a little bit mixed up right here. Is that bad that I say that for people who like haven't taken chemistry? I'm not trying to like say or anything. I'm just trying to like let you know. Dr. Wells will say in Try 5, like I'll only tell you the truth. But this is just some definitions that we need to know. And the first one is that free energy is defined as the energy content in a system that can be converted to do work. So all that's saying is free energy is just energy that we can use to do something with. And that's called Gibbs free energy. So the test question is probably going to be like, what is Gibbs free energy? Or what is that definition? You have to be able to put Gibbs free energy. I don't know who Gibbs is, but I wish we could just say that it's just free energy and not Gibbs free energy. We're just going to keep it at that. So we have our substrate, okay? Say we have, I'm sick of saying substrate, that like never works. Say we have glucose, all right, and we're going through glycolysis. We need to get to glucose 6-phosphate. We talked about hexokinase as the enzyme doing that earlier, right? We'll get to like what it actually means. But say we've got glucose, and we need to get to its product, glucose 6-phosphate. The ground state, or just kind of like the amount of energy that is in glucose, we'll just say is right here, is at halfway up this thing. But it's more stable at glucose 6-phosphate. Right, so it wants to get, it's like when you're drinking, say you've had like 3 Red Bulls, and you're like all hopped up, right, and you're like shaking, and you're like got too much energy. All you want to do is just like be able to calm down and relax, or like when you're taking a test and you're all like psyched up, and you just want to like relax and take the test and get all the questions right. That's kind of like ground state, or starting ground state and our ending ground state. So you're starting off with a higher energy, and then you're ending with a lower energy, okay? So, and the enzyme is what helps get you from this higher to this lower ground state. Oh my gosh, okay. So, glucose 6-phosphate. Glucose is your G1. G just is Gibbs free energy. So, that's your G1, your ground state energy of the substrate. So your glucose or your Red Bull. And then then you have your product ground state here, or your energy level there, and that is your G2. And the difference between those is just G1 minus G2. He could ask you that. But just know that G1 minus G2 and negative is preferred in most cases, just because we're going from higher to lower along this y-axis. So that's what delta G is. So if you ever see delta G, that's all it's talking about, is just where'd you start on your energy level and where did you end on your energy level. That's it. If you, let's see, if that is negative, so if that delta G equals negative, that is exergonic. All right, so we started here and we're getting there. So we can say that some energy exited, it left, so we got more negative. So that's negative. And then the opposite of that, where is it? Where is it? Looking for the word endergonic. Who sees it? Good one. I don't see it. Whatever. So if the negative delta G, exergonic. If delta G is positive, endergonic. And endergonic. Endergonic. So energy is entering. All right, so in that situation, it would be like S would be here and P would be like up here. So it gained energy. Why this is important is exergonic, these reactions are favorable. All right, we want energy to leave. Question?
Is that the same as
It's the exact same thing, pretty much. Yeah, it's the exact same thing. So either heat or energy leaving or being gained. What we need to know about that is that exergonic, when delta G is negative, it means that the reaction is more favorable. It's happy that we're going from Red Bull state to chill out state. Whereas if it's endergonic, we're putting energy into glucose or into the system or what have you. And so we're kind of going from chill out state to Red Bull state. And that's harder to do. Kind of tough. Do we have questions?
Is it less stable than at the original ground state?
So this is less stable than that is on this picture. So the lower the ground energy, the ground state energy, the more stable it is. Good. We'll get more into that. We'll get more into that in chapter 7, but that's a preview of that.
Okay, so it's harder to go from negative to positive to put energy in.
Yes, it's harder to put energy into it. It's less favorable to put energy into it because it's kind of going from more stable to less stable. So that's why it's easier to just go from less stable to more stable, because that's what we're trying to do. It's just kind of trying to reach homeostasis as much as possible, to put another word in there.
How would he ask that?
Exergonic reactions. I think he'll ask more of it in chapter 7, to be honest with you. But he could just ask you, exergonics are more favorable or negative. Probably exergonic and negative delta G. Or he could just ask you what the definition of delta G is, which is G1 minus G2.
Or gives free?
Or what Gibbs free energy is, which is free energy that can be used to do work, just what's available to us. It's like, this is like money. Like, just pretend like the energy is money. Like, we can spend the money that we do have, whereas we can't spend the money that we don't have. Pretend credit cards don't exist. Cool. We have more important fish to fry than that.
Do we know anything about the activation energy?
Getting to that. Getting to that. All right. So it's actually this first line. Enzymes increase the rate of chemical reactions by decreasing activation energies. All right, so just to scroll down, say we have glucose here, glucose 6-phosphate here, right? Without hexokinase, in order for this reaction to happen, we have to put in that much energy, which is a lot. Okay? Very hard to do. It's very hard to put that much energy to make that reaction happen. However, when we get hexokinase and we use that enzyme, the only amount of energy that we need to use is that little bit right there. So comparatively, it requires a lot less energy and a lot less effort to make reactions happen in our body if we're using enzymes, because it lowers the activation energy. And the activation energy is just the amount of energy that is needed to make a reaction occur. Are those blank faces that I'm seeing? Okay, so the transition state, are you just talking about like this ESEP? Or, okay, so the transition state is just was what we talked about here. These are just different transition states. So here we have our substrate. We have our enzyme binding to our substrate. And then here we have our product that is made. And then here we have just our product. So the transition states are just the different binding of the enzyme to the substrate, and then the product that's formed still bound to the enzyme, and then the release, and it's happy all the way down here. That didn't answer your question, did it?
Is that like the amount of energy needed to make these two bind together, and then in order you have to have a little more energy just to make that the actual product, and a little more energy to release that product?
Yes.
Okay.
So what she said, which is way better than what I said. So transition states are just different. It's like they're kind of checkpoints within it, right? So here we have our substrate. You need this much energy to put it in to bind to the enzyme. So transition state here. Then you need this much energy to actually make the product, and you need this much energy to separate from the product. So those are your different transition states.
So the one that goes higher is without any of the substrate, so it'd be a lot harder for the reaction to happen.
It'd be without any of the enzymes. There's no enzymes present. So that's all substrate with no enzyme. Yeah, so that'd be like you taking a trip to New York City walking versus in an airplane, right? Like you could do it both ways, but we prefer to use the airplane, right? This isn't like 1700. Cool, so the difference between the energy levels of the ground state and the transition state is the activation energy, which is what we talked about. We can make these go faster if we increase the temperature and increase the pressure, right? So when we exercise, our body heats up just a little bit. And because we're producing heat, and that actually helps make our body perform better when we're warmed up, right? When we do something, we warm up first, athletically, for those of you who are athletically in charge. Or like even for those of you who are in band, right? You warm up and then you play. Same principle. We're really laughing at band. Come on, y'all. It's cool. Only the cool kids did it. That's not true. That is not true. So our activation energy, moral of story, TLDR, activation energy can be lowered by adding a catalyst, which is just an enzyme. Too long to read. Too long, didn't read. So when someone puts like a big post and they summarize it. Anyway, role of binding energy. Decreases activation energy because we don't want to go all the way to the top. And a lot of this happens with just our non-covalent forces, right? All our enzymes bind to substrates non-covalently. Don't want it to be permanent. Don't worry about it. Could increase. All right, so we're going to be dealing with some graphs now, right? This is exactly what we wanted, some graphs to make science better. That was sarcasm. So we have our substrate concentration on our x-axis. We have our speed of the reaction occurring on our y-axis. So let's see. So just more starting material, so like more glucose adding, and then more, like the faster the reaction's happening. What we need to know from this is that, it's on the next page. Actually, no, it's right here. So we have a plateau here at the top. So what that means is we only have a certain amount of enzymes in our body. So say we have 100 enzymes, right? And say we have just like 10 glucoses here. All right. Well, we're going to go. We're going to have like 90 left over. So those reactions are going to happen pretty quickly. But not as. Sorry. I got so much material. Just trying to calm myself down. So, all right. We have 100. Say we have 100 enzymes. All right. And we only have 10 glucose. That's not going to happen very fast, right? Because the chances of a glucose binding, being in the right spot in a space to bind to that enzyme is pretty low. But if we have like 1,000 glucoses and only those 100 enzymes, the chances of one of those glucoses binding to the enzyme is really high, right? Because there's just so many of them that it's bound to be in that same general area to where they can actually react with each other. Does that make sense? Okay? But, so the fewer substrates we have, the lower the velocity is going to be. But the more substrates we have, the higher the velocity or the rate of that reaction is going to happen. But there's a plateau here at the top because we only have that 100 enzymes. So we can only go so fast. So say all 100 are used at the same time, we can't go any faster than that. We're at like max capacity. So that's where our velocity max comes into play. So Vmax. This 1/2 Vmax is going to come into play here in just a little bit. All you're going to need to do is remember that equation. And we'll get to that. What we need to know on this page is this equation, delta G, so it gives free energy, is equal to negative RT natural log of our equilibrium constant. I could explain it to you. Just memorize that equation, please. It'll be easier.
Did we do like equation or method solve?
You're not going to have to solve anything.
So you just have to know the formula.
Just know the equation.
Where's it for? Like, you don't have to explain the process. You're just saying what's the word definition.
That's how we're going to equate if our reaction was exergonic or endergonic.
Okay.
It's pretty much how we're going to determine if it's positive or negative. So if we're releasing or gaining energy. Cool. Just trying to get through it. I'm so sorry. There's just a lot. He gets like 5 days. Need to know the Michaelis-Menten equation down here. This was actually a national board question. We went over this in ours as well. Need to know the Michaelis-Menten equation. So know that Vmax is on top, and Km plus S is on bottom. This was on our test when we took it. But also knowing this definition too, that Km is equal to 1/2 Vmax. He'll go over that in class with y'all tomorrow. So to ask him about Km, he just should like drill that into you. But knowing Km is equal to 1/2 Vmax, that question is going to be like, what does Km equal? And then you're going to pick 1/2 Vmax, and then you're going to get it right, and you're going to the next question.
1/2 what?
1/2 Vmax.
Okay.
I never understood this. Did not understand it. I don't think it mattered. So if anything, I think you just have to relate. I think I saw something where like Vmax was on the y-axis, but that's just something that I saw from like an old national boards question. But I don't even think they said that happened like very, very rarely. Cool. Okay, so there we have time now on our x-axis and our product concentration, so the product's being made here. And we have, we'll just say like 1 substrate, that's like micromole, don't worry about it. Say we have 1 thing, 2 things, and 3 things, all right? All this is saying is that the more substrates you have, over time, the more products you're going to make. Or the less substrates you have, the less starting materials you have, over time, you're going to make less, right? Like if you make a bet that the Broncos are going to win the Super Bowl, if you bid $5, you're going to get however much of return on investment. But if you put like your life savings on it, you can potentially get more return on your investment. I'm seeing a smiling that like maybe the Broncos are going to lose. Actually, like no one's betting on the Broncos. It's ridiculous. If you read any of those articles, everyone's on the Panthers. Cool. That's all that's saying. Not that important. So this is kind of getting into the specificity of it. Like we talked, like specificity, always specific in our body. We have to have that certain pH. They talked about what's the pH of our blood? 7.35, 7.45. That was on boards too, so know that. So enzymes have their own specific pH that they have to work at as well. So it's got to be the right pH. It's got to be the right temperature, right? Can't be too hot, too cold. You got to have the right substrates to bind. And this is just saying, like, if it's cold, you're not going to get anything done. But at this heat, it's going to be like max efficiency. That heat, that's too hot. It's not going to work. Cool. Need to know these next 3 things. So these are the different types of inhibition. Dr. Sarkar loves to know how things are inhibited or regulated or controlled in any manner. The only tough part here is the name, trying to get uncompetitive and non-competitive right. But y'all are smart. Competitive inhibition. This type of inhibition occurs at the active substrate binding site of an enzyme. What the hell does that mean? Okay. We got pictures. So this is like it's going to slide over, whatever. All right, so say you have like you and your brother or your sibling, and there's one toy, right? Only one of you can play with that toy at one time because you're like 5. So it's they're both competing for that same thing, that same spot. And so what happens is the substrate here, the substrate can bind here, and then the enzyme can go on and work. Or this inhibitor can come in and bind. Your sibling can take that and turn it off or deregulate it. So the thing with competitive is that both the substrate, the thing that the enzyme is meant to convert into something else, and the thing that turns off the enzyme, both go to the same spot. It's competitive. They're fighting over it at the same time. Okay? So they directly bind to the substrate's binding site. Cool. More graphs. All you need to know for these graphs, a little bit of memorization, is that the Vmax remains unchanged and the Km increases. So, just gotta know it. Just gotta know it. There's a chart at the end that has all of it all at once. Just gotta know it. Come talk to me tomorrow when we have more time, and I'll talk to you about it. Gotta know it. So Vmax unchanged, Km increases, competitive. So cool. Uncompetitive inhibition. Uncompetitive inhibitors affect the catalytic function, but not substrate binding. So how this is different is that substrate is allowed to bind to where it needs to without fail. So substrate binds, but then this inhibitor binds at a different spot than turning it off. So that'd be like you're playing Xbox, and then your brother comes in and like smashes the Xbox. Or like you're, or like if you're on your computer and you like, so you turn your computer on, you can log on, but then someone hacks your computer and like turns it off. That would be uncompetitive, right? There's no competition for that active site. There's no competition at all. But what's important to know is that that substrate binds first, and then the inhibitor binds. And what we need to know for this one is Vmax decreases, Km also decreases. And how he's going to ask that on the test is also decreases. So uncompetitive, they both decrease. The velocity of the enzyme working, so how fast those reactions happen, and what half of that max velocity is, both decreases. So if you want to remember it like a U, this like has like two down arrows, they both decrease. Uncompetitive, both decrease. Lastly, we have mixed or non-competitive. So this one's a little bit different. So the mixed inhibitor binds at a separate site, but can bind either when the substrate is there or it's not there. So that's why I made sure to say over here, uncompetitive, substrate binds first, then inhibitor binds. Here, that enzyme can be turned off at any time. And once again, it's non-competitive, so it's binding to a site different than the active site. So substrate can bind, and then inhibitor combined, or inhibitor combined, and then substrate combined. So both of them can kind of come and go, and when that inhibitor is not there, enzyme's working. Boom, perfect. Inhibitor binds back, turned off. That's non-competitive. And what you need to know for that one is Vmax decreases, Km unchanged. I know this is getting like really monotonous. And this was like really difficult for me, like sorting these out. It's just taking the time to look at it. All right, so we're going to stick, let's just go through that with a band example or a fan example. We'll go sports and band. How about that? All right, so we've got a vuvuzela, right? We're at the World Cup circa 2012. Is that when? 2010? Wherever. You got a vuvuzela. You're in the stands, right? You and your buddy both. Y'all combine your money to buy one. Okay. Y'all both want to cheer, be loud. Everyone else is on theirs, so you'll compete over the vuvuzela, right? Who can, whatever, like do that. So, so pretend I'm the substrate and I get the vuvuzela, like the enzymes got me. Boom, I got there first. I picked it up first. I blew on it. I win. Well, my buddy picks it up first. Next time, I can't blow on it now, so he's got it. So he's the inhibitor for me. Cool. That's competitive. Uncompetitive would be like a mute, okay? Or say he like, okay, question.
Kind of story. I'll just tell me if it's wrong or not. But
Okay.
Competitive. So I know me and my sister, we were younger, we were racing to get shotgun. So say someone was racing to get shotgun first, and whoever got it had to settle for the backseat.
Mm-hmm.
Is that kind of how it is? Or?
Pretty much, yeah. Yeah, you're both fighting for that same spot. Cool. For uncompetitive, with the vuvuzela, say I got it, and I'm cheering, whatever, how the vuvuzela sounds. I'm terrible at impersonations, accents, what have you. But then, like, my friend stuffed like his shirt like in the end of it, so I couldn't blow out any sound, right? So that pretty much turns that sound off at all. What?
Like you have it, but you can't use it.
Yeah, I got it, but I can't use it. It's like worthless. It's turned it off. But then if he takes that shirt out at the end of it, sound comes out. I'm a happy fan.
That's non-competitive or
That's uncompetitive. So then we have non-competitive. All right, so for non-competitive, he can either put the shirt in whenever he wants to, or when I have it up to my mouth. So I could be playing it, and he could just be like a really terrible friend, and I like wouldn't know. So I'm playing it, and he puts it in, or he can just have it like waiting there for me. So I think I'm ready to go, and then it doesn't work. So non-competitive, there's no chance that I can play that vuvuzela if that shirt's in it at any point. But if you take the shirt out, I can still use it.
Basically, if your friend's there, you can't use it.
If my friend gets to it first, pretty much no, I can't use it at all. That worked really well for the first two, and then I realized that wasn't as good as the last one. I tried. I didn't hear that. I should have walked up earlier. Probably. Ask it again.
Let's say you had like an estrogenic property that had estrogenic qualities.
Okay.
And it was endogenous, and it gets into the body somehow. It can function as a substrate of estrogen, and subsequently bind to enzymes that would activate upon estrogen and then increase the effects of estrogen when in fact you wouldn't want them to do that.
Yes. Yeah. All right, sorry for that. Okay. This chart here at the top of the page summarizes all of that. So if you're a chart person, kind of like keeps all the information all in one spot, which is helpful. Irreversible inhibition. Irreversible is going to be our covalent bonds. So covalent bonds are stronger than all of our other bonds, right? Than our ionic or our polar interactions, or than our hydrogen bonds or what have you. So whenever we see a covalent linkage, those are going to be more irreversible. And an example would be the aspirin through the COX pathway. You'll learn about that in Try 3. Mechanisms of regulation. Skip. Let's see. What we really need to know here, pretty sure we're just going to go through all that. We're just going to skip that. What we need to know here are different types of covalent modifications. He asked this on our exam. He didn't ask it. I don't think he asked it last try, but I know he asked it on our exam. Just knowing that we can, we do have some reversible ones, and they are these 7. Okay, so types of reversible covalent bonds, we have phosphorylation, adenylation, acetylation. He won't, if anything, he's going to say phosphorylation, adenylation, methylation, ADP ribosylation, maybe ubiquination, maybe. So he'll say, like, which of the following is an example of a type of reversible covalent modification. You'll have to pick one of those, or he'll say which of the following isn't, and it'll probably be something like, the answer will probably be something like carboxylation, something like that, because that's not one of those 7. Sorry if that wasn't visible. So the test question would probably say something like, the answer choices would be phosphorylation, adenylation, methylation, and carboxylation. And you'll just need to know that carboxylation is not like the others. Yeah, just know the names. I mean, because in theory, you already know the structures, right? So phosphorylation, you're adding a phosphate. Adenylation, that one might be a little harder. Methylation, you're adding a methyl group. You're adding a ubiquinone, we'll learn that later. These are all, chapter 4 is wonderful in a lot of ways, but it sucks in a lot of ways. So obviously this chapter was how many pages? A lot, right? So really, really pay attention to this chapter, because this is a chapter that is kind of tricky. We'll go over it next time, promise you, just trying to get through it this time. Really try to pay attention as much as possible to Dr. Sarkar. Listen to him in lecture, what he repeats 2 or 3 times. If he's repeating it 2 or 3 times, he usually is pretty good about sticking to that on the test. So just, it'll be okay. On this page? I don't think there's a lot that's important on this page. I don't think so. Cool. Questions? Sorry that this was so frantic, frenetic. What other fast-paced word we can use? Question.
All chapter 4 is going to be, well, I guess you're going to get that. We're not going to test over all of that once you sit it, right?
He should do all of chapter 4 on the test.
He has an hour to finish like 20 pages.
Yeah.
Wait, he's only on page?
He's only on page 55.
So the test might be, what does it say on y'all syllabus? It says 1 through 4 on the syllabus, right? Okay. Well, if he flies through it all tomorrow, which he might, you've seen it. Yeah. I can't support that. openly. I can support it now, though.
When are you going to do
I-
another two?
Yeah, Friday at 11
11?
in here. Question? I'm just going to leave the dum-dums out, and if y'all want to come grab one, come grab one. Y'all were troopers today. Hopefully an hour. Here. Y'all don't have class, right? At 11? Okay.